Welcome. My name is Johan Mellqvist. I'm a professor in optical remote sensing, and I will guide you through this presentation and how to measure the composition of the atmosphere from the ground with optical absorption techniques. In this lecture, we will discuss why it is interesting to measure atmospheric composition. We will also discuss some general spectroscopic theory that is being used in the measurements. Some applications of light absorption measurements will be shown, from the infrared to the ultraviolet region. I will also describe a global network for monitoring of the global atmosphere. The gases in the atmosphere play an important role for life on the Earth's surface. For instance, they impact the global temperature, which in turn affects, for example, moisture and global circulation. They control the amount of ultraviolet radiation that penetrates through the atmosphere. They cause local and regional air pollution. Last of all, they may have negative effect on health. The energy of molecules and atoms correspond to discrete energy levels. A higher energy can show up as an increasing rotation of the electrons around the atomic core, and more vibrations and rotations between the atoms in the molecules. Electromagnetic radiation interacts with different energy levels in the atoms and molecules. The type of interaction depends on the wavelength of the radiation, as seen in the table. I will discuss the ultraviolet to the infrared wavelength region between 200 nanometer to 15,000 nanometer. When a molecule or atom absorbs light in the UV visible region, the incoming electromagnetic radiation changes the orbitals of the outer electrons, and at the same time the radiation also changes the vibrations and rotations of the molecules, which causes fine structures in the absorption spectra. The corresponding physics occurs for infrared light, but here only vibrational and rotational changes of the molecular energy levels occur. In absorption spectroscopy, broadband light passes an absorbing gas, and then it is recorded by a spectrometer. The shape of the obtained absorption spectrum is compared to reference spectra from a database using mathematical analysis. The wavelength position and shape of the absorption band is usually unique for each species, making it possible to identify and quantify different compounds. Sometimes their features overlap, and then it is required to match several reference spectra simultaneously to the measured spectrum. Absorption spectroscopy is based on the Beer-Lambert law, which states that light which passes through an absorbing gas will be attenuated exponentially with the distance through the gas. The amount of absorption at a certain wavelength is proportional to the absorption cross-section, usually denoted sigma. This is a parameter that includes the physics of the energy transition which is involved. If several species absorb at the same wavelength, the individual cross-sections add linearly. By measuring the ratio of the incoming intensity I0 and the intensity I along the path, it is possible to derive the column C times L in the cell. If L is known, also the concentration can be obtained. In open-air measurements, I0 is often taken at a nearby non-absorbing wavelength. The Beer-Lambert law in the previous slide is only valid for short path lengths in particle-free air, for example a laboratory cell. For longer path lengths in the atmosphere, the light is also attenuated due to scattering on the molecules and particles in the path of the light, resulting in that fewer photons hits the detector. The light scattering on molecules is called Rayleigh scattering, and on particles scattering. The Rayleigh scattering increases strongly with shorter wavelengths, and this is why the sky is blue. The scattering has a much weaker wavelength dependence, depending on the particle size, and it causes the white haze one can see over polluted cities. Let's look at how the absorption cross-sections in the UV visible region look for some of the gas species which are present in the atmosphere. The first spectrum corresponds to ozone. This species is present in the higher atmosphere and shields us against UV radiation from the sun. It is also pollutant in the lower atmosphere. SO2 and NO2 are pollutants produced by combustion processes, causing respiratory problems and acidification. Formaldehyde is produced from degradation of volatile hydrocarbons, and it is an intermediate in the production of photochemical smog. Bromine oxide is produced from the degradation of flame retardants, halons, in the high atmosphere, and it plays an important role in the destruction of stratospheric ozone. HONO is a nighttime radical that is produced from degradation of NOx, and this primarily occurs on surfaces such as asphalt or concrete. Here you can see how light at different wavelengths is attenuated when the light is sent through the air of a city. The wavelength region corresponds to the ultraviolet to the infrared region. As you can see, scattering by particles is the dominant reason for light attenuation in the visible region, above 370 nanometers. In the ultraviolet region below 370 nanometers, the scattering by molecules and absorption by ozone is also very important. In the near-infrared region above 700 nanometers, water vapor attenuates strongly at several wavelength bands. Here's a list of molecular species which are active in the production of photochemical smog and which can be measured using long-path UV-visible spectroscopy. The technique is often called DOAS technique, which means differential optical absorption spectroscopy. Thanks for listening to this first part about ground-based optical measurements of the atmosphere.